So our next speaker is Professor Anurag Srivastava again. He's going to be presenting, his work in validation and test validation.
All right, so thank you again, and I'm going to talk about Testbed now. If you look at all the cyber events that's happening, we need to do two things, and those two things are basically tools, which I already talked about. And the second thing is validate those tools in real time or in offline mode, a scalable manner, so that we can deploy those tools, right? So focus today is, in this talk is going to be on testbed for validation. And I'm going to talk about two testbed. So one is what I call Electromechanical Simulator, which is OpenDSS and GridLabD kind of things, interfaced with me in it. Both are cyber physical. And they're hosts where we can put distributed coordination or distributed optimization or even centralized optimization kind of algorithms. There's a Python wrapper around this. And the second one is RTDS based, which is electromagnetic, or could be Opal RT2 here, in real time with HIL lab. So let me first focus on first one, which is the electromechanical simulator. And we're using it for this project, that we're working with the DOE on this. So in this one, we have OpenDSS. Maybe I'll go back a little bit. So we have OpenDSS with representing the distribution system, and Mininet representing the cyber or network system, and then several different applications which runs on these. So we can run restoration algorithm, we can run voltage control algorithm, and we can do it either centralized or hierarchical or distributed here. And if we do a cyber attack kind of simulation, it would also be in one of these hosts, which is tied to each of these. So we can see the impact on set of algorithm. So each host here basically are representing like a node. And Python wrapper that we have developed is connecting the different system, which is cyber and physical. Socket communication used between the host and also host that communicates against each other is also through Python. So here's one example. As you see in the top, there is a cyber attack application, which is kind of model that we have done, which will represent a different, using that we can implement different kind of cyber attack models, so man in the middle attack and denial of service attack. So we try to do that, and one of the hosts here in a cyber network, which we can actually map to any, like, let's say if it's a voltage control, then a physical device will become malicious and model as in a step for a man in the middle attack scenario. And another scenario that we use is denial of service attack. And once we do that, then we will be able to get all the different kind of results, on voltage or current, because this simulator in the power grid is very much detailed. So we can see over the time that how the attack is impacting. So for example, this one, the green line was normal, and this is for voltage control. But once the attack happens, you can see that the voltage is not being stabilized and changing, which is, of course, will be very different for different kind of attack. One thing by doing these kind of experiment, we realized that centralized application will not be that much resilient as compared to distributed. And there is a reason for that, because distributed, when each of these nodes are talking with neighbors to implement a control and optimization algorithm, those will be less and less impacted compared to if we do a centralized application, right? Because those are more closely tied and coupled. Now the second one is Testbed 2, which is electromagnetic real-time simulator. So here we do have a RTDS, which models the system, and then we do have this distribution system communication model, which is in NS3 developed. And we do have a physical sensor and controller. So this is how it looks like. We are still populating more devices here. So RTGS and a couple of SEL devices. And then we also have a BeagleBone, where microcontroller, where you can implement distributed algorithm or any other kind of control and tie it with RTDS. The data, the way it is flowing, so there's a GPS which is synchronizing for the PMUs and PDC and different devices that's connected. There's two software-defined networking here, and then also HMI and also automation controller that is connected here. So the data flow is, you have a basically physical system model here, and then we have a hardware PMUs and sensor, and GTNet, which is representing the SCADA data, is flowing through this and going to NS3 communication simulator. You can call it emulator because it's really transferring the data. This communication simulator will finally feed it to some kind of data concentrator. Here we are using OpenPDC. And then we also have resiliency tool. So this one is CPSAM tied in the control room. So the control room is, even though it's small, but this is how it looks like. We have divided the control room into two parts. One is the power grid control center, and one is network operation center, which is for cyber. And both are displaying the different material, and our students and our representing operator will sit into these two different control rooms. So we are logging a lot of these data as it flows, not only for the physical system, but also for the cyber system. And we use, different kind of analysis, data analytics that we can run on those cyber data and also physical data. So here's an example, which is looking at the substation traffic data and running some analytics and then running some tools on these, so we can see the cyber anomaly and we can see the physical anomaly separately. And once we find a correlation between cyber anomaly and physical anomaly, then we can try to correlate and see that what kind of event it is. Is it a cyber, or it is a physical, or it is a physical fault? And then finally can take action based on that. So all of these are basically going and being stored into a Splunk server that we have integrated into this Testbed. And the good thing is that being with the physical system, these are more elastic, right? So if you do a cyber attack model, any of these, related to GPS or data flow here, all of these will be logged, and we can see the changes to run our different tool, right? So there are several different tools that we are integrating into our own. Sync AED is a sync failure anomaly and event detection tool, which is several different base detector integrated into Ensemble to detect the physical kind of anomaly. And then same thing with the Splunk server, and on the different stage at substation, we are running this distributed anomaly for cyber. All right, so we'll stop here, and just to summarize, we do have developed two different cyber power test bed. One is for scalable loss system, because in OpenDSS we can model several thousand bus system. So like 10,000 bus system we have done, and then also in scalable manner, Mininet can also go for a loss system with several instances. And the other one, which is electromagnetic RTDS, has a limitation on size because of RTDS, cost limitation, that how many basically rack we can build in our lab. So we can do a smaller system like IEEE 33 bus system, and that we have done there. And this is again tied in real time with several different sensor controller and with NS3, and we also have integrated all the network operation center kind of environment and power grid control center kind of environment to observe the physical and cyber data in that case. We can also do the real attack with electromagnetic real-time HIL simulator, and that's what we're trying to do with all these things. And we can, so we call it, simulator emulator with HIL, because these are all integrated with the cyber logging. And then finally, as part of this project, we are trying to test and validate our cyber physical resiliency metric and decision-making process into this. Okay, well, thanks again for several different sponsors and my students for doing that work. Any questions?
Thank you so much, Professor Anurag, for the presentation. Yeah, we have time for a couple of questions. First thing, I would like to ask one of the questions from the attendees virtually. So the question is, what software do you use for the substation traffic analysis?
Yeah, so there are several. I mean, in terms of capturing the data, all these are logged, and again, Splunk is the one where we are collecting all the data together, right? So Wireshark can be used for capturing the traffic substation data, and there are several other software available. So we have tried several, but the one is Wireshark is the most common. And once we collect that, then there is another tool which is to analyze the data to see the cyber anomaly, and that is our which we call machine learning tools, supervised and unsupervised, that we have developed in our lab.
Okay, thank you so much. Any other question from the attendees?
Thank you very much for the great presentation. This is more of a general question. Is there any limitation for using the digital twin, especially when it comes to resilient operation? Is there anywhere that cannot rely on the test bed and then we have to use other algorithms? Is there any noticeable limitations?
Yes, yeah, a lot. In fact, when we say digital twin, we need to look at, the first requirement is there has to be a real system, right? Which we're trying to imitate. In all our test bed, we do not have complete data from real system to imitate, right? So digital twins should exist not in test bed, but more in utility control environment, right? For digital twin, only the model is not a requirement, right? So only the model will not give you digital twin, because with that we need to imitate everything else, which is control, not only power grid model, but also maintenance of those models, and also real-time data fetch. And the closest thing that we can get is training simulator, right? That exists in the electric grid operation center. So training simulator is getting real data, right? The measured from the field. It also has a model which has good representation. I will not say complete digital twin, and so that will be closest thing, but it does not reflect all the control that is possible. For example, if you have remedial action scheme in the field, it's not reflected into that in the other model. And even if you look at training simulator, most of them are a steady state. Dynamic is just started. So I would say that we are very, very far away from digital twin, even in the utility data environment. If you try to do in the test bed, it will be several years of effort to really to get to digital twin. And there is reason for that. If you start modeling the system, we all know that it's either second order approximation, right? So higher order model does not exist. And if you try to do that, then it's not scalable. So what is the threshold when we start calling model as a digital twin is a discussion topic. And right now, if you look at and ask utility, as we include more and more polytronics with switching, our model in the field is going away from its outcome, basically what we can measure and what we can simulate. And the reason is very obvious, because by adding polytronics and switching, we are adding more nonlinearity in the system. Model is always single order or second order or maybe third order we can get to, not very high. So as we add more nonlinearity into the system, our model is going to go away. And that's, if you look at, like, let's say an RTDS model, which is being used by utility cases, and I have several discussions with vendors who try to do that. With the Polytronics, they see a clear difference between and the 1996 blackout was a very good example, which shows that how the oscillation was different in the field and how it was in the model. And since then, we have made a lot of progress in modeling capabilities. But if we start analyzing each and every component, we always do approximation, and that's the only way to be scalable. So digital twin, maybe 2 decades away.